Welcome back, Marauders. Today we're going to talk about section 1.2, mass spectroscopy of elements, my favorite section. Mass spectroscopy of the elements is the way that we figure out the average molar mass of elements. So we have the periodic table, and you guys have seen that the periodic table has the average atomic masses, and you've probably noticed that the average atomic masses are not whole numbers. And you may have wondered how that's possible. If we know that atoms have to have a whole number of protons and a whole number of neutrons, and they each have a mass of essentially one atomic mass unit. How is it possible that we have all these different decimal numbers for the average atomic masses? And so let's look at an example. Let's look at an example of boron. Boron has two isotopes, so two atoms with different numbers of neutrons. Boron 10 has 5 protons, 5 electrons, and 5 neutrons. And boron 11 has 5 protons, 5 electrons. Then what makes it different is that it has 6 neutrons. So boron 11 is a little bit heavier. It has a mass of 11 atomic mass units versus boron 10, which is 10 atomic mass units. And so if we had a naturally occurring sample of boron, some of it would be boron 10, some would be boron 11. And what we'd find is that it's not a 50-50 mix. If it was an exact average, it would split right down the middle. We'd have an average atomic mass of 10.5, but we don't. If we look at the periodic table, we have an average atomic mass of about 10.8 or 10.81. Why is that? Well, the reason for that is that one of the isotopes, boron 11, is a lot more common. It's about a 4-to-1 ratio between how common boron 11 is and boron 10. And so we have a weighted average where we have just 20% of the atoms having a mass of 10 atomic mass units, and about 80% of the atoms having an atomic mass of 11. And so the weighted average is 10.8, which is about, I rounded the numbers here to make it a little simpler for the example, but it's about the average atomic mass that you see on your periodic table. How do we collect data? How do we know that this is true? What evidence do we have for the fact that there are different isotopes? And how do we figure out how abundant each of the isotopes is? Well, the process we use is mass spectroscopy. And the way it works is we take a sample of atoms, like our boron, and it's just a random, naturally occurring sample with some of the heavier and some of the lighter isotopes. We turn that sample into ions so that they have a charge, and since they have a charge, they'll be attracted to a magnet. And so we pass them by these magnets. This magnet's pushing them away, this one's pulling it towards, and so it bends them around the corner here, and then they land over here on some kind of a detector. And so the atoms, or the isotopes of an atom that are lighter, get deflected more. They turn a lot and they land over here. The ones that are heavier, they keep going a little further and they're deflected less by the magnet, so they're detected over here somewhere. And so if we do this for my sample of boron, we see that just one of those lighter boron 10 atoms ended up over here, and 4 of the heavier boron 11s ended up over here. So it's the way we separate them is by passing them by these magnets, and then there's a little detector down here at the bottom, and it counts how many of the lighter ones, how many of the heavier ones are hitting in each location. And so the mass spectroscopy will produce some data that looks like this. So the mass spec data for boron would look something like this. There'd be a graph, and it would show a small peak here at a mass of 10 atomic mass units, and then a taller peak here at 11 atomic mass units. So whenever you see a graph like this, along the y-axis, you're going to have relative abundance. So that's how common each one of the isotopes was. And along the x-axis, you're having the different molar masses, so 10 or 11 in this case. Here's the data. It says that there were 23 of the lighter ones and 100 of the heavier boron 11. We can use that to calculate the average atomic mass. And so if we take the fraction of them that are the lighter, 23 out of the 123 times that lighter mass, 10 atomic mass units, and then plus the fraction that are the heavier ones, 100 over 123 of the heavier ones, we get that 10.81, which is the same number that we see on our periodic table. So this is how what evidence we have that different isotopes exist, and how we're able to measure the abundance of each one of the isotopes is with mass spec data. The kind of questions that you're most likely to see on a chemistry test with mass spec data is they could give us an element. So we have an element given, and they give us the different isotopes of zirconium that are possible. And so there's zirconium 90, that has a mass of 90, that has an abundance of 51.5%. And then there's an isotope 91, 92, 94, and 96. And then each of the abundances is given right there. And so they might ask us to draw or match this up with a graph of the mass spec data. And so we'd want to first figure out how many isotopes there are. There's 1, 2, 3, 4, 5 different isotopes. The first one has a mass of 90, so there'd be a peak here at 90. How tall would that peak be? Well, that would be the tallest peak. It would go up to 51.5 on my relative abundance scale here, because that's the most abundant one. And then at 91, that isotope's a little bit less common, 11.2. So you see that there's a shorter peak here at 91 atomic mass units. And then we just continue showing the other peaks representing the different isotopes. So we have 1, 2, 3, 4, 5 different peaks because there's 5 different isotopes. They are each starting at, or along the x-axis, they're showing what those different molar masses are, or the masses of those different isotopes are. And then the heights of those show which one's most abundant. So this one's the most abundant, this one is the least abundant. And if we took the weighted average of all these, we could get the average atomic mass of zirconium. Other times they might give us the data and ask us to figure out what the average atomic mass is or what the element is. So here we see that we have 2 isotopes. One has a mass of 35, the other has a mass of 37. So we know that we're going to be looking for an element with a molar mass somewhere in between 35 and 37. So you can look on the periodic table and see what elements that might be. Without even doing the calculation, we can tell that the average is going to be closer to 35 than it is to 37 because this one is more common. So we think it's going to be probably less than 36, a little bit closer to 35 than it is to 37 since that's the more common isotope. If we do the calculations, we can get a little more precise answer here. So 3/4 on this graph of the particles are that lighter 35 atomic mass unit isotope. And then 1 out of every 4 are the heavier with a mass of 37. So we take that weighted average, we get about 35.5. And so if we look at the periodic table, what does that come closest to? It looks like that's closest to the average atomic mass of chlorine. So this looks like a sample of chlorine. Again, these numbers are kind of rounded, or we're just kind of approximating. This one looks about 3 times taller than this one. And so it's not exactly the mass of chlorine on the periodic table, but it's definitely closer than any of the other elements. So I think that's all I have for mass spec data. Make sure you get some practice, and we'll see you next time.